Let's go JavaScripting! Hi everybody and welcome to another exciting edition of Boring JavaScript. I'm your host, the Virtuoid, aka Mike Smith, and today we're taking a look at bit shifting in JavaScript. That's right, we're going to get down to the nitty-gritty of the individual bits within your variables. We're going to show you how to shift things to the left, we're going to show you two ways to shift things to the right, and we're going to show you why on the earth is it important to know this stuff. You want to see how they work? Let's get started. So before we start shifting bits to the left or to the right, let's talk about what a bit actually is. A bit is the smallest possible measurement of computer memory, and it has two states. It's either on or it's off, and those states are represented by the numbers 1 or 0, because we can understand 1 or 0 much better than we can stand on or off. Now, what we'll also end up doing is that we'll usually group all these bits together into things like called nibbles or bytes and things like that, and then group these bytes further together into even larger structures to be able to represent things like numbers. In fact, I've got something like that on the screen right now. In JavaScript, a number, an integer number, both a signed integer and an unsigned integer number, is represented by 4 bytes of information, and that happens to be 32 individual bits. There are 8 bits per byte, and there's 4 bytes, so therefore there are 32 bits. And these are numbered 0 through 31, 0 being what's called the least significant bit. And so what happens is that when you get a number like 1, 2, 3, 4 in this particular case, it will then convert that into binary notation and determine what bits to turn on and what bits to turn off. So in this case, I've got the first bit turned on to 1. Now, why is that the first bit? Because this happens to be the 0th bit, if there is such a word as 0th, but that's basically what it is. This is the 0th bit. So in 1, 2, 3, 4, the first bit is on, the 0th bit is off, the second bit is off, the third bit is off, the fourth bit is on, that would be the 6th bit is on, the 7th bit is on, and the 10th bit is on. All the rest of them are off. That computes to 1,234. Now, how do we know that? Well, there's only two possibilities for each bit, a 1 or a 0. So to do the calculations here, you need to know a little bit about exponents. This number right here, that particular bit represents 2 to the power of 0 because it's the 0th bit. This number represents 2 to the power of 1, or the number 2. This bit right here, which is the 7th bit, represents 2 to the power of 7. This bit is 2 to the power of 10. So if we were to take 2 to the power of 10 plus 2 to the power of 7 plus 2 to the power of 6, plus 2 to the power of 4, plus 2 to the power of 1, and add all those together, I guarantee you we're going to get 1,234. So that's how you can kind of cross-check that. So this is what we're going to be talking about. We're talking about shifting bits to the left or shifting bits to the right. To the left means we're going to be taking these bits and moving everything from the least significant bit to the most significant bit. When we shift right, we're going to be taking everything from the most significant bit, this from the left-hand side here, and going all the way to the right or to the least significant bit. So now that you know what bits are, let's get into shifting bits to the left. So now let's take a look at shifting bits to the left, and it's extraordinarily easy to use. First of all, what I've got here is I'm going to have a number. I want to shift that number off to the left. And to do that, what I do is use that particular operator, a double less than sign. And that basically tells JavaScript to shift all the bits to the left, or basically shift bits from the least significant bit over to the most significant bit. It's going to take basically my number, shift the bits, this number of bits. So in this particular case, I'm taking the number 2 and I'm going to shift it by 1 bit. So if I want to shift it by 2, 4, 6, 8 bits, well, it doesn't really matter. I just change that number there. And that's it. That's all that happens. So what I'm going to do here in my code is I'm going to print out my number, and then I'm going to print out the left shift number and show you the difference between the two. So let's flip back over to Node. And let's type in Node. Let's actually type it in correctly, Node left. So here is my number 2, and that is the binary representation for number 2. Now, how do I know it's number 2? Well, that's 0 to the power, that's 2 to the power of 0, which is a 1, but since it's number 0 there, we're not calculating that. There's a 1 here, so that's 2 to the power of 1, so that's the number 2, and That's it. So we know that's 2. When I left shift the number, as you can tell here, it was 0010. It is now 10100. So it is now taken that number 1 and shifted it off to the left, moving it from the least significant to the most significant bit position. And it's saying that the number should be 4. Well, let's find out. Well, that happens to be that's 0th, that's the 1, that's the 2th, that's the second position. So that would be 2 to the power 2, or 2 times 2, which is equal to 4. So that basically shifted it off to the left by 1 spot. So to show you that it will work with 2 spots, let's go back to the code here. And on number 4, line number 4, I'm going to change that to 2. So this should now shift it 2 bits to the left. Let's find out if that worked. Let's flip over to node again, and let's type in node left. Again, here's my number 2, and sure enough, it went by 2 bits, but now the number is 8. Why? Because that position is the 3rd bit, and 2 to the power 3 is 2 times 2 times 2, which is 8. Again, that's how you just like I showed you earlier in the bit one, that's how you calculate it. So that shows you how the left shift works. But I do want to show you a gotcha that you need to be aware of. Let's flip back over to our code, and you're going to need to be aware of this in all of the anything that we're going to be working with here, all this different shifting. I'm going to change that back to 1, and I'm going to put a negative number inside here. So as you kind of noticed there, that every time I shifted off to the left, it basically multiplied the number by 2. So when I shifted off by 1, 2 became 4. When I shifted it by 2, 2 became 8. So that was 2 times 2 times 2. So every time I shifted things off to the left, every single bit basically multiplied the original number by 2. And that's kind of an easy way to remember how all this stuff works. So if that is the case, I should expect this number to be negative 4, what number is that? 4 billion, 1, 2, 4, I don't know, negative 4 billion something or the other. So now we got negative 2,147,483,648. We're going to shift it by 1. Let's see what happens. Let's go back over to node. We'll clear the screen off here. Go node left, and no, it went to 0. Why did it go to 0? Well, this is something you need to remember. This is within JavaScript, and it actually is within a lot of different languages. Whenever you have an integer number that is negative, they always usually reserve the very last bit of the number as being the sign bit. So the number that you're actually working with here is only 31 bits long, because that last bit is going to be a sign bit. If that number is 0, it's considered a positive number. If that number is 1, it's considered a negative number. So that's the only exception to the rule here, is that when you're working with signed numbers, which JavaScript is, obviously, because you can have negative numbers there, that last bit is always number 1. So we did a left shift here. When we did the left shift, that shifted the 1 out and made it disappear. So from JavaScript's particular point of view there, I'm now positive. So I have basically changed my number from a negative to a positive. So that's one of the things you've got to be very, very, very careful about when you're working with negative numbers and you're doing shifting, is that you can very easily turn your number from negative to positive or positive to negative without knowing what's going on there. So that's kind of that's one of the catches you're going to get with doing the left shift. Now, what about the other way? Let's take a look at that next. So now let's take a look at the right shift. Now the right shift will shift all the bits from the most significant bit down toward the least significant bit. And it works exactly the same way as the left shift, except that it has 2 greater than signs instead of 2 less than signs. And this basically says, just like with the left shift, take the number that you passed in, shift the bits off by this number of bits, and store that into the variable that you're assigning it to. And that's it. So in this particular case, I'm going to start with the number 2. I'm going to do a right shift by 1 bit. And just like with left shift, when you shift it by 1 bit, that basically multiplied it by 2. If you do a right shift by 1 bit, it basically divides by 2. So I should expect my right shift number to be 1 while my regular number is 2. So let's take a look at node and see what happens. And yep, sure enough, there we go. I went from the number 2 to the number 1. And the verification is that this is 2 to the power of 0, which is always 1. So yep, that's 1. This is 2 to the power of 1, which is 2 times itself, which is 2. I just said that wrong, but anyway, so it's number 2, so we know that's correct. So if we change it now to 4, we should end up with 2. Let's flip back over to Node. Get my hands mixed up there. And yep, we went from 4 to 2 because that's 2 to the power 2, which is 4, and that's 2 to the power 1, which is 2. So what about negative numbers? Well, let's find out. Let's just take this to -4 and shift it by 1 and see what happens. Because remember, we have that 1 at the very beginning at the bit number 31, and that's the signed bit. So if everything gets shifted, this is going to turn into positive, right? Let's save that. Let's flip over to Node. Let's clear the screen off here. Let's go Node right. And I went from -4 to -2. By the way, this is what a -4 looks like. We're talking about 2's complement here. Don't worry about what 2's complement is. Google 2's complement. You'll figure out why this is all a whole bunch of different ones here. But notice here that we went from -4 to -2, which is the correct thing. We divided it by 2. So what happened? Well, when you do a right shift, what JavaScript will do is it will sit there and say, okay, now I know that I'm going to be moving that number 1 out of the, or I should be moving that number 1 out of the 31st bit, but that's part of my signed bit. So when you do a right shift, it actually keeps the sign of the original number. So if this happened to be all zeros, for example, except for that one final number 1 there, and you do a right shift, you're still going to get nothing but all zeros with the number 1 at the very end. So if you start with a 0 in the 31st bit, in bit number 31, and you do a right shift, if you start with a 0, you're still going to have a 0 there. If you start with a 1 and you do the right shift, you're still going to have the 1. So a right shift keeps the sign at all times when you do the right shift. And that's, again, one of those important things to know with the right shift. So, how's that going to work if you need to work with all of the different bits? For instance, let's say you had an unsigned integer that you were working with, where you need to have that 31st bit to be part of the number itself. You can't sit there and have that number stay the same no matter what. So how do you fix that? I'll show you that next. Okay, so it's all well and good doing the right shift where it keeps that signed bit, but what if you are working with unsigned integers, which you could be working with quite often? Well, that's where you have what's called the unsigned right shift. And let's take a look at that one. Instead of being 2 greater than signs, it's now 3 greater than signs. And that tells JavaScript is, hey, just shift everything to the right and automatically put a 0 at the very beginning at the bit number 31 to basically still make it into 32 bits. So everything gets shifted over regardless of whether it's signed or not. So I've got a -2 here. And then I'm going to shift that over by 1 bit, and I'm going to do an unsigned shift. So let's take a look and see what happens there. Let's go over to Node. Let's type in Node unsigned right. And so I started off with my -2, and here's the 2's complement representation of -2. My right shift number now is 2,147,483,647. Why? Because remember, the 31st bit is the signed bit. But the unsigned right shift says, I don't really care if it was signed or not to begin with. I'm just going to shift everything over and throw a 0 at the very end. So, I mean, at the very beginning as the most significant most significant bit. So it throws 0 there. So now JavaScript is sitting there going, oh, okay, hey, we got a positive number now. So a positive number with all these bits set is 2,147,483,647. So if you have to work with unsigned integers, then you want to use the unsigned right to be able to ignore that sign bit at the very beginning, and that way you'll never ever go wrong. So now I've taught you about the left shift, the right shift, and the unsigned right shift. So what in the world would you ever use these things for? That's next. Okay, so why learn left shift and right shift and unsigned right shift? Well, if you ever notice that when you download a file, sometimes they'll have some sort of hashing algorithm or some sort of numbers saying that you need to be able to do a calculation on this particular file, and that calculation needs to match their calculation or their hash. And if it doesn't match, then the file may have been corrupted. Well, all that hashing algorithm, in this case what I'm looking at here is what's called a CRC or a cyclic redundancy check, are ways to be able to calculate the integrity of a particular file. And to do that, it uses a significant amount of bitwise operations, which we'll cover in another Boring JavaScript, and a lot of shifting. Now, I've pulled up just a random code here of how to calculate what's called a cyclic redundancy check, a 32-bit cyclic redundancy check. And again, this is something that allows them to be able to calculate a large string or a file and come up with a particular number that then you can check when you download it off the internet, and you can check it against their number, and if they don't match, there's a problem there. So what they've done here, this is an example of where they're using, for instance, the XOR bitwise operator, which is something we'll cover again in a later JavaScript, but here's where they're using the unsigned right shift. And again, this is unsigned right shift of 1 bit. So in all the calculations they're doing here, they are using all the XORs and all the shifting and everything to be able to get whatever values they need to do that will satisfy the algorithms that are required for, in this case, a CRC32. If we go a little further down here, here's some more examples. Here's an example of a signed right shift. Here's another unsigned right shift. If we go a little further down, even into this big mess down here, bunches of unsigned right shifts. Here's an XOR. Here's here's where was it? There was one here. I wanted. There it is, right there. Here's a left shift that they've got here. So they're using different combinations of left shifts. Here's a signed right shift. Here's an unsigned right shift. So, all these calculations are done on these CRCs, on these hashing algorithms, on cryptology, for example, in order to be able to apply whatever algorithms are needed to be able to ensure the integrity of files or to ensure the integrity of messages that are passed across to you. So this is if you're really into things like cryptography or checksums, hashing algorithms, things like that, you'll be using a lot of these bitwise operators, which again, we'll show you another JavaScript, but mostly with these shifting algorithms, the bit shift left and the shift right and the unsigned shift right, to be able to implement the algorithms you need to be able to, in this particular case, ensure the integrity of the file. And that's all there is to shifting bits to the left and shifting bits to the right. I hope you enjoyed our video. Hope it didn't bore you to death. Please make sure you click on the like button below or click on the subscribe button to be able to get notifications whenever we release new Boring JavaScript videos like the bitwise operators that we'll be doing here fairly shortly. Also, you can go to www.boringjavascript.com to see all the videos we produced, or www.thevirtualoid.com to see everything that we have. Thanks again for watching, and we'll see you later.